Year 13, Chapter 9, Further Differentiation, Lesson 1, Differentiating Exponential Functions. So let's recap what we know from the content you've covered back in Year 12. And you know that if y equals e to the x, then dy by dx is also equal to e to the x. At every point on the exponential curve, the gradient is equal to the y coordinate. Now we can generalize this a little bit further and say that if y equals k e to the x, where of course k is some constant, this then tells us that dy by dx is equal to k e to the x, and we'll be using this result as we learn how to differentiate more complex exponential functions. So let's start with an example. Y equals 4e to the 3x. Now the first thing that you need to notice is that this is a composite function. Can you see the component parts here? We have x, which is multiplied by 3 to give us 3x. And we then do e to the power of this, e to the power of 3x, and we then multiply by 4. So we get 4e to the 3x. But the key components here are the fact that x is multiplied by 3, and then we take e to the power of 3x. So there is your composition of two functions. Now, how do we differentiate a composite function? Well, we use the chain rule for doing this. And what we're going to do is set up the full chain rule process here and then explore what is actually happening. So remember, we need to identify the inner function, which of course is the 3x. So u is equal to 3x. And we then need to set up the fact that y can be expressed in terms of u as 4e to the power of u. We then need to differentiate both parts of this with respect to the variable in question. So du by dx is equal to 3, and dy by du, well, it's an exponential function, a simple exponential function. 4e to the u would differentiate to give us 4e to the u. Now, the chain rule then tells us that dy by dx is equal to dy by du multiplied by du by dx. Now, we know that dy by du is 4e to the u. You can see that in blue. We then need to multiply by du by dx, which is 3. And this then gives us 12e to the u. But of course, to finish this, we need to replace u with what it is in terms of x. So the final answer, 12e to the 3x. And as we did when we learnt about the chain rule, in the first place, start looking to see if you can see the connection. Y equals 4e to the 3x. dy by dx is equal to 12e to the 3x. Can you see the connection between the function and its derivative? Because if you can, then you're starting to see the beginnings of the quick chain rule applied to an exponential function. Let's have a look at another example. Now, it's another composite function. Y equals a half e to the 9x minus 1, and the composition comes from the fact that we have 9x minus 1, and then we take e to the power of that. There's the two steps in the process. The half is really just a multiple at the end. So let's identify the innermost function, which is u, which is 9x minus 1, and then we can say that y is equal to a half e to the power u. Differentiate both parts. Du by dx is equal to 9, and dy by du is equal to a half e to the u. Remember, a single exponential function e to the u differentiates to e to the u. So what can we now say? Well, dy by dx, according to the chain rule, is dy by du multiplied by du by dx. So let's bring in these two parts. So a half e to the u multiplied by 9, which gives us 9 over 2 e to the power of u, 9 over 2 e, and instead of u, we want to feed back in from here e to the 9x minus 1. And again, as I said previously, look at the original function, y equals a half e to the 9x minus 1. Can you see the connection between this and the derivative? So 9 over 2 e to the 9x minus 1. So let's have a look at a third example, and we're going to look at the example y equals 3e to the x squared plus 4. Can you see that that is a composite function? So we have x squared plus 4 as our inner function, and then e is raised to the power of x squared plus 4. So we'll use the full format of the chain rule again. U equals x squared plus 4, our inner function. Y equals 3e to the power of u. And let's differentiate both parts of this. So du by dx is 2x. dy by du is 3e to the u, and then dy by dx is equal to dy by du multiplied by du by dx according to the chain rule. So that's 3e to the u multiplied by 2x this time. So this simplifies to give us 6x e to the u, but of course we want to make sure we replace u with what it is in terms of x. So the answer is 6x e to the x squared plus 4. Let's put that in brackets for clarity. So could we do this using the quick chain rule? And the answer is yes, we can. Look at the original question, the original function that is being differentiated over here. Now, it's an exponential function, so exponential functions differentiate to themselves. So e to the x squared plus 4 essentially differentiates to give us e to the x squared plus 4. But of course, we also have this component of 6x. Now, where does the 6x come from? Well, part of that is just the 3 that was there originally in the question. But the other part is a 2x. Now, where does 2x come from? It's the derivative of the inner function x squared plus 4. So how does the differentiation work? Well, y equals 3e to the x squared plus 4. That's the function. I can write down dy by dx as follows. Let's look at all the parts of this. So the 3 is just present in the answer. Exponential functions differentiate to themselves, so we get e to the x squared plus 4 in our answer. But we need to multiply by the derivative of the innermost function, and the derivative of that is 2x. So here are all the components of the derivative. And of course, this takes us to an answer of 6x e to the x squared plus 4. And we can see that from the previous examples as well. Remember, y equals 4e to the 3x. Well, dy by dx, we can use exactly the same process. 4 is just a multiple in the answer. Exponential functions differentiate to themselves, so we get e to the 3x. But we then need to multiply by the derivative of the inner function, which is 3. And then go back to the first question, you can see we got the answer of 12e to the 3x. So, crucial points: exponential functions differentiate to themselves, and we need to multiply by the derivative of the innermost function. Let's look at another example so we can check that we fully understood all of this. Y equals 2e to the 5x minus 4x squared. Now, can you see that's an exponential function? It's also a composite function, but overall it is an exponential function. So dy by dx is equal to, so remember the 2 here is just a multiple, so it's going to be part of the answer. Exponential functions differentiate to themselves, so the answer will also feature e to the 5x minus 4x squared, but we must multiply by the derivative of the innermost function, which is 5 minus 8x. So putting all those components together takes us to our answer of 2 bracket 5 minus 8x e to the power of 5x minus 4x squared. And here's our answer. Now, let's look at another example. Y equals e to the x plus 3 all raised to the power 7. Now, this involves an exponential function, e to the x, and it's also composite because we're doing e to the x plus 3 and then raising to the power of 7, but it's in the form of a power function overall. So yes, it involves an exponential function, but overall it's a power function. It's something being raised to the power of 7. So let's take a look at using the chain rule to differentiate this. We're going to do this in 2 ways. We're going to use the formal long format of the chain rule, and we're then going to use the quick chain rule to do this. So first of all, of course, if we're going to use the long form of the chain rule, we need to identify the inner function. And what is our inner function? Well, it's this. It's e to the x plus 3. So u equals e to the x plus 3. And what is y? Y is u being raised to the power of 7. And as soon as you write this down, you should then see why this is a power function. It's y equals something raised to a power. It's not y equals e to the power of something, which is an exponential format. Du by dx is then equal to e to the x, 3 differentiates to 0, and dy by du is 7u to the power of 6. Now, don't forget the format of the chain rule. Dy by dx is equal to dy by du multiplied by du by dx. So that gives me 7u to the power of 6 multiplied by e to the power of x, which gives us 7e to the x u to the power of 6, or 7e to the x, and then in place of u, remember, e to the x plus 3 all raised to the power of 6. Now, can you see how we could have got there using the quick chain rule? Let's take a look at the original function. Y equals e to the x plus 3 all raised to the power of 7. It's a power function. So when we differentiate something that's a power function, we need to multiply by the power and then reduce the overall power by 1. So that's where the 7 brackets e to the x plus 3 all to the power of 6 comes from. But we then multiply by the derivative of the innermost function, which in this case is e to the x. Now look at this. That's exactly the same as the answer that we have here. So really important that we understand what's going on here. So we multiply by the power. We have reduced the power by 1 afterwards, and then we multiply by the derivative of the inner function. And that's how we can apply the quick chain rule. So let's generalize this. Now, we've done a little bit of this previously. A power function is a function of the format y equals, and then we have f of x, which could be any function, all raised to the power of n. Now, dy by dx, we know, is then equal to n multiplied by f of x to the n minus 1. So we multiply by the power. We then reduce the power by 1. And of course we have to multiply by the derivative of the inner function. So we need to multiply by f dash x. And that's how we differentiate using the quick chain rule for any type of power function. But what about a function that is an exponential function overall? Well, what would that look like? Well, that would look like y equals e to the power of f of x. So you can see the difference between the two types of function here. Now, dy by dx, using the chain rule, we know that an exponential function differentiates to itself, so we get e to the power of f of x. But what we then have to do is multiply by the derivative of the inner function, so we multiply by f dash x. So again, a slight difference here. Exponential functions differentiate to themselves. But we must make sure we multiply by the derivative of the inner function in the composite. And it's important that we can use these rules quickly and efficiently. So we're going to have a go at 4 examples. Have a look at these. You can either watch along with the video or pause and try and differentiate these yourself. In each case, you're going to use the quick chain rule, but you have to identify whether you're dealing with an exponential function overall or a power function overall. In each case, is the example of the format e to the power of something overall, whether something is your innermost function in the composite, or is it of the format something to the power of some number, where of course the something might contain an exponential function. Let's take a look at the answers. Now, the first question is an exponential function, and the inner function is 5 minus 3x. So dy by dx, the 4 is just here as part of the answer. Exponential functions differentiate to themselves, so we get 4 multiplied by e to the 5 minus 3x. But we then multiply by the derivative of the inner function, which is negative 3. So the answer is negative 12 e to the 5 minus 3x. Question 2. This is a power function. First question was an exponential. This is a power function. So dy by dx, we need to multiply by the power of 5, reduce the overall power by 1 to 4, and then multiply by the derivative of the inner function. Now, this is where you then have to use the chain rule again, because e to the x squared itself is another composite function. So this is why you have to be so quick with being able to use the chain rule effectively. So how do I differentiate e to the x squared minus 2? Well, the 2 will just differentiate to 0, so it's really the e to the x squared I'm worried about. Well, e to the x squared in itself is an exponential function. So I need to remember that exponential functions differentiate to themselves. So that would be e to the x squared, but then I need to multiply by the innermost function here as well, or the derivative of the innermost function rather, and the derivative of the innermost function is then 2x. So you have layer upon layer of composite function here, a really interesting question. So we end up with 10x e to the x squared brackets e to the x squared minus 2 all to the power of 4. Question 3, this is another power function, but you may wish to rewrite this as 8 minus e to the x all to the power of a half. So dy by dx, we need to multiply by the power of a half, reduce the overall power by 1 to negative a half, and then multiply by the derivative of the inner function. Well, 8 differentiates to 0 and e to the x differentiates to itself, so we have negative e to the x. So our final answer to this question is negative a half e to the x, 8 minus e to the x all to the negative a half. And the last question, again, this is another power function, but we'd rewrite it as this first of all to the power of negative 1. Then dy by dx multiplied by the power, reduce the power by 1 to negative 2, and then multiply by the derivative of the innermost function, which is just e to the x. So our final answer, negative e to the x plus 4, all to the negative 2. So we're going to finish off by having a look at a few examples using the product and quotient rule involving functions which use or make use of exponentials. So we need to identify first of all that this is a product. You can see the clear product of two separate functions. So let's identify these two functions. I'm going to say that u is x. U could have been e to the x, but I've chosen u as x, and v is equal to e to the x. Differentiate both of these with respect to x. Du by dx is 1, and dv by dx is, of course, e to the x. Now, what does the product rule then tell us? The product rule then tells us that dy by dx is equal to u multiplied by dv by dx plus v multiplied by du by dx. So this then becomes very easy to set up. So we want the pairs across here and here. The product rule is always easy to remember for that reason. It's symmetrical, and because of the addition, it means it's very easy to set up. So we have x e to the x plus e to the x, as du by dx is 1. And always useful, if possible, to factorise, especially if we're looking for stationary points in a question. So we have another product, which means we'll be making use of the product rule in a minute to differentiate this. I'm going to identify u as 2e to the x. I'm going to identify v as 8x plus 1 all cubed, so that's this portion here. And I'm going to differentiate both parts. Du by dx is 2e to the x, and dv by dx, now this is where we've got to use the quick chain rule to differentiate, and that's why we have to be so good at using the chain rule in a quick and efficient manner. So we get a power function here. So to differentiate this, multiply by the power, reduce the power by 1, and then multiply by the derivative of the inner function, which is 8. So we get to an answer of 24, 8x plus 1 all squared. So dy by dx, remember, is equal to u multiplied by dv by dx plus v multiplied by du by dx. So again, you're looking for these cross pairs here. Let's put everything together. So we have 2e to the x multiplied by 24 brackets 8x plus 1 all squared plus 8x plus 1 cubed multiplied by 2e to the x. So what can we factorise? Well, we have a 2e to the x and a 2e to the x, and we also have, if we look at part in brackets, 8x plus 1 squared, 8x plus 1 cubed, taking the lower of the two powers. So let's take out 2e to the x, and let's take out 8x plus 1 squared. I'll put in the big square brackets for clarity. And then what would go inside these brackets? Well, we need a 24 in this part here, and then we simply need an 8x plus 1 here. So let's finish this off. This then gives us 2e to the x, 8x plus 1 squared, 8x plus 25. A much more useful format for the derivative if we then have to calculate a gradient value to find the equation of a tangent or normal, or particularly if we're searching for stationary points. So here's my last example, and we can hopefully all see that the best way to differentiate this is to use the quotient rule. In theory, we could rewrite it so we have 2x minus 1 to the negative half in the numerator and then use the product rule, but actually, as we've seen previously, it's much easier to use the quotient rule. So we need to identify our u, which is our numerator, and identify our v, which is our denominator. And let's start differentiating. U equals e to the x, du by dx is e to the x. V is the function in the denominator, 2x minus 1 to the power of a half, and then dv by dx, we need to differentiate using the quick chain rule, because of course, you should be able to see that this is a composite and it's a power function overall. So multiply by the power, reduce the power by 1, and then multiply by the derivative of the inner function, which is just 2. So this then gives me 2x minus 1 to the negative a half. dy by dx then equals, using the quotient rule, v multiplied by du by dx minus u multiplied by dv by dx, and the whole thing is divided by v squared. So let's put everything together. So v multiplied by du by dx, first of all, is this. So that gives me e to the x multiplied by 2x minus 1 to the power of a half. And then I want to subtract u multiplied by dv by dx. So that's e to the x multiplied by 2x minus 1 to the negative a half. And then the whole thing is being divided by v squared. And of course, v squared is simply 2x minus 1. Now, I'd like to simplify this, so I'm going to start off by dividing both parts in the numerator by 2x minus 1. So that gives me e to the x, and then that's going to become 2x minus 1 to the negative half. Think of that as a power 1 there. Subtract your powers as you do the division. And then e to the x to the power of 2x minus 1 to the power of negative 3 over 2. Now, some serious factorisation needed here. E to the x can, of course, come out of a bracket, but we then need to take the lower of the two powers, which is 2x minus 1 to the negative 3 over 2. Now, inside the bracket, we then have, for the purple part to start off with, 2x minus 1, and then we have subtract 1. Check as you multiply back in your head that you can see exactly how this would expand to give us the top line, or the line above. So this then finalises as an answer as e to the x, 2x minus 1 to the negative 3 over 2, and then 2x minus 2. Now, a last step really, I think, would be to factorise out the 2 from this final bracket here and bring this out to the front, but I seem to have run out of space. Might be feasible just to squeeze it in here for clarity at the very end.